Outer area. There are more than 1 trillion small, icy masses beyond Neptune's orbit in a dark, cold region outside the solar system. Objects in the Kuiper belt and dwarf planets fill the area outside of Neptune. Even at great distances, a large group of comet nuclei has formed a massive, spherical cloud called the Oort cloud. Kuiper belt. A flat area of various objects known as the Kuiper belt is located about 6 billion kilometers from the Sun. The outer edge of this vast belt is just as far from the Sun. The first object in this belt is the QB1 1992, which was discovered in 1992. More than 1,000 objects are known in this area, and tens of thousands of other objects are in this area. Most of the objects in this area have a combination of rock and ice, and their appearance is not spherical. They are usually about 1,000 kilometers in diameter and take more than 250 years to orbit the Sun once. Oort cloud. The Oort cloud surrounds the circular region of the solar system's planets. The outer edge of this giant spherical cloud, made up of comet nuclei, is 1.6 light-years from Earth. About half the distance from the Sun to the nearest neighboring star. The cloud contains more than 1,000 billion comets that orbit the Sun independently. Comets with short orbits originate from the inner part of the cloud, and those with long orbits form the outer part of the cloud. Dwarf planets. The largest objects within the Kuiper belt are dwarf planets, and the heaviest known example is Eris. Eris is a world of ice and rock, discovered in 2005 and completes its orbit round the Sun once every 550.9 years. Pluto is slightly lighter but larger than Eris and was the first object to be discovered beyond Neptune's orbit in 1930, and by 2006 was the farthest planet from the Sun. Pluto's status and classification changed after a new definition and classification of solar system objects called dwarf planets were adopted in August 2006. Some astronomers have long considered Pluto a strange and incompatible planet. In fact, unlike the outer planets of the solar system, which are mostly made of hydrogen, Pluto is only 2,376.6 kilometers in diameter, of which 70% is rock and 30% is ice. Its surface temperature is -230 degrees Celsius, and it orbits the Sun in an orbit that is unlike any other planet. The planet's orbit around the Sun has an angular difference of 17.2 degrees with respect to the solar system's plane. A handful of dwarf planets are known so far, and many are expected to be discovered soon. Similar objects in the Kuiper belt are also known as plutoids. The term, coined in 2008, distinguishes them from dwarf planets in the solar system. New Horizons spacecraft. We know very little about the world beyond Neptune. The New Horizons spacecraft was the first probe to study these distant objects from the Sun. Launched in January 2006, the spacecraft passed Jupiter in 2007 and met with Pluto in the summer of 2015. With the help of a set of radio telescopes based in the United States, Japan, and Spain, the spacecraft's ground-based crew followed it. We were ready to receive information from it. The spacecraft's camera sent its first image of Pluto to Earth as it approached the dwarf planet. The rest of the instruments provided details of the color and surface composition and a map of its temperature variation. They also analyzed the composition, structure, and temperature of the atmosphere. The spacecraft was also looking for signs of the atmosphere around Charon. Charon is the largest moon on Pluto. Because the New Horizons spacecraft could only study one Pluto hemisphere, scientists used images from the Hubble Space Telescope, currently the best observational instrument for Pluto, to decide which hemisphere is better for New Horizons. After examining Pluto, the spacecraft diverted to a new target in the Kuiper belt. In January 2019 met with a mass called 2014 Mu69, which appeared to have been formed by the collision of two stray space clumps. New Horizons now continues to travel in the Kuiper belt. Comets. Comets are remnants of materials that were not used in the process of building planets at the beginning of the solar system. The total mass of all comets is estimated to be several times the mass of Earth. The orbits of comets orbiting the Sun are different from those of planets orbiting the Sun. Their orbits are elongated ellipses that are not on the solar system plane and form different angles with them. A star passing through the Sun's neighborhood could disrupt the Oort cloud, pulling some comets out of the cloud and pulling them toward it or placing others in paths that lead to the inner and central part of the solar system. Those comets that travel close to the Sun produce glowing heads and huge comets. As comets approach the inner part of the solar system, their temperatures rise, creating comets of dust and gas. Some glowing comets can be seen with the naked eye in the Earth's sky every decade. The heart of a comet has an irregular structure and appearance. It is composed of a rotating nucleus of dusty and dirty snow. Typically, the diameter of this core is between a few hundred meters and several kilometers. The dirt mentioned in the previous sentence is particles of silicate rocks that have formed the crust and mantle of the inner planets. The snow mentioned is mainly water ice. But out of every 20 molecules, one contains compounds such as carbon dioxide, carbon monoxide, methane, and ammonia. Outside Jupiter's orbit is a comet, cold and dormant. But as it gets closer to the Sun, solar radiation penetrates through the dust layers that surround the nucleus, causing its material to convert directly from solid to gas. The volatile gases pressurize the surface dust and push it out of its path. This behavior creates a spherical cloud around the core called the coma. As the amount of solar wind increases, the pressure increases, creating two tails behind the nucleus that develop on opposite sides of the Sun. The closer the comet gets to the Sun, the longer the comets. Large dust particles are released and detached from the nucleus, slowly following the nucleus or separating from it and remaining in orbit around the Sun, forming a ring of dust and dust particles around it. When the Earth cuts these rings in its orbit around the Sun, the collision of these dust and small particles with the upper layers of the Earth's atmosphere creates meteors and meteor showers in the Earth's atmosphere. Astronomers have identified more than 200 comets with periods shorter than 20 years and another 2,000 comets with longer periods. The solar system is estimated to have at least 1 trillion comets. Most of these nuclei do not travel close to the Sun and remain unknown. These comets form a very large spherical region called the Oort cloud. The fact that comets entering the interior of the solar system form their comets means that their nuclei must be losing mass. That is, they are falling apart. Each time Halley's Comet orbits the Sun in its 75-year orbit, it loses a layer 2 meters deep around its core. With this trend, the entire comet nucleus will remain around the Sun for the next 200,000 years. In fact, before 1986, astronomers had no idea what the core of a comet looked like. In February of that year, the European Space Agency launched the Giotto spacecraft to image the core of the Halley Comet as it approached the Sun. Since then, more sophisticated missions have been designed and deployed to the cores of other comets. The cores of comets are so small that they cannot be seen in detail with the help of ground-based observatories. To see them, we have to send spacecraft to visit them. The Giotto, sent by the European Space Agency, was the first spacecraft to visit the nucleus of a comet. The spacecraft traveled across the solar system and passed 600 kilometers from the core of the Halley's Comet. This transit occurred on March 13, 1986, 5 weeks before the comet reached its closest distance from the Sun. Halley orbited the Sun in the opposite direction to Earth and the spacecraft. For this reason, the spacecraft and the comet were approaching each other face to face at a dangerous speed of 245,000 kilometers per hour. Giotto took measurements of gas and plasma around the nucleus. The spacecraft barely survived the comet dust. Giotto made the first images of the comet's core. Comet surface mapping was very limited. Because only half of Halley's core was exposed to sunlight, only half of it faced the spacecraft. However, Giotto recorded the surface details of Halley, showing that its core is mostly smooth and has very few hills or valleys. The comet was losing 3 tons of mass per second. This dark, potato-like mass with a diameter of 15.3 kilometers rotated around itself almost once every 3 days. In January 2004, NASA's Stardust spacecraft passed through the inner coma of Comet Wild 2. They sampled the dust with the help of aerogels it carried with it. The chamber of these particles was sent to Earth and returned to Earth with the help of a parachute for further study and analysis. These samples confirmed that comets are indeed ancient objects. But what surprised the scientists was that these objects are made of various materials. In addition to the amount of ice formed in areas beyond Neptune's orbit and comets, these samples contained some rock material that formed at very high temperatures near the Sun. This not only provided a clearer understanding of the importance and formation of comets but also provided clues as to the origin of the planets. Until 2014, we could only take snapshots of 4 comets as they passed. But the European Space Agency's Rosetta spacecraft launched to Comet 67P/Churyumov-Gerasimenko was the first to place an orbiter around the comet's core. The Rosetta spacecraft met the comet in August 2014. That is when the comet was 600 million kilometers from the Sun. It then remained in orbit and traveled with the comet. All areas of the comet were carefully surveyed and mapped, which continued hour by hour for several years. Rosetta sent its last signal to Earth in late September 2016 and went off forever. In 2014, a lander called Philae landed on the fragile surface of the comet's core. The surface provided 10 scientific tools to study constituents inside the nucleus, including a radar tool for intranuclear analysis and chemical analysis. Due to the lack of activation of its protection system, this lander got up several times and sat down on the comet's surface again. Eventually, Philae was able to send images and data from the comet's surface to Earth. Still, due to the unstable situation and landing in an unknown part of the comet, it was practically impossible to continue its mission.